Our speaker for today is Dr. Arindam Chowdhury. Professor Chowdhury obtained a BSc in chemistry from University of Calcutta and a master's from the Indian Institute of Technology, Kanpur in 1997, which was followed by a PhD in 2003 from Carnegie Mellon University, Pittsburgh. After a postdoctoral stint at Columbia University at New York City, Dr. Chaudhary joined IIT Bombay in 2006 as an assistant professor, where he established the first single molecule fluorescence spectroscopy and dynamics laboratory in India, with the intent of conducting interdisciplinary research. Currently, he is serving as a professor of chemistry at the Indian Institute of Technology Bombay. Amongst other recognitions, Dr. Chaudhary serves as the editorial advisory board member of Chemical Communications (RSC) and the ACS journal Chemical and Biomedical Imaging. Over the years, Dr. Chaudhury's research focus has been to elucidate origins of spatiotemporal heterogeneity in soft materials, biomolecular assemblies, and semiconductor nanocrystals, as well as develop microscopic tools to probe complex systems. Since 2015, Dr. Chaudhury's group have ventured into the study of instability of optoelectronic properties of halide perovskite nanomicrocrystals films, which are being used to develop next generation solar, photovoltaic, and light emissive devices. Th- Thank you so much, Dr. Chaudhary, for joining us here today, and the stage is all yours now.
And for the very, very nice introduction. Um, uh, it's kind of embarrassing sometimes, but today I would like to talk to you guys, to everybody, about something that we have been working on over the last 8 years or so, and something that I kind of stumbled upon in 2015, and then started working on it, and started and continued working on it. Now, before I move on, let me thank the people who were involved in this work. In my lab, I have two teams. One group of people work with soft materials, another group of people work with hard matter or crystals, nanocrystals, and other crystals. So these are my co-workers who are involved or have been involved, starting with Nitin and Tejumani. I have omitted somebody's name here, Ramya, who actually was doing the work initially, the very initial stages, but Nitin and Tejumani's work is mostly the focus of this talk. And the collaborators that have been actively involved in assisting me and getting me going in this problem is Angshuman Nag from ISR Pune, and also Professor Shaibal Sharkar, Professor Mohammad Aslam, and Professor Ashwini Yella, who are all from IIT Bombay. Shaibal is in energy science, Aslam is in physics, and Ashwini is a professor at materials science. And the funding for this work has been generous support from IIT Bombay and SERB DST, Government of India, as well as the National Center for Photovoltaic Research and Education, which is in IIT Bombay. It's a picture of my group, and this yellow ovals show the two people. This is Nitin on the left. Let me see whether I can go to printer, laser pointer. Nitin on the left, and Tejumani here is on the right. These are the two people whose basically PhD thesis is what I'm going to talk to you about today. And this is the current group of mine that I have in IIT Bombay. So our lab essentially works on single molecule spectroscopy and single nanocrystal spectroscopy. Combined together, I use the term single emitter spectroscopy, but we have been looking at semiconductor nanocrystals of various kinds, especially quantum dots and quantum rods and wells, such as core shell nanocrystals or dope nanocrystals or alloyed nanocrystals. And in 2015, we started working on perovskite. So this is the story that I'm going to talk to you about today. Apart from that, as I mentioned earlier, part of my group works on soft materials, including biophysical problems, using single molecule spectroscopic methods, as well as single molecule FRET. And another small group has been working on developing methods for sensing applications. and different kinds of biosensing, especially using spectroscopic methods or spatial result spectroscopic method. But the overreaching idea, the goal, the focus of our lab is essentially to probe spatiotemporal heterogeneity in physical parameters in complex systems. And to do that, we have been developing different kinds of methods of measurements and analysis. Now, what is the real advantage of probing the subensemble? I'm just going to give you a very, very small example here. If you have collected an emission spectra, I'm assuming there's a lot of graduate students in this crowd, and this talk is pretty much geared towards them. And if you ever taken an absorption or emission spectra, you may have always seen something which looks like this, something with a double hump. And in solution, this kind of double hump can originate from various reasons. It can be due to molecules which inherently have two transitions which are overlapping. Or it's possible that if you actually go in and look at different smaller sections or sets of molecules that are present in your system, you may end up getting different kind of spectral signatures. And that's essentially the idea of probing the subensemble. If you have heterogeneity, in the sense that if you have green and blue and purple and orange balls, which are the color of light that is being emitted by molecules, for instance, then you may end up getting different spectra depending on what is the size of the spot that you are, or the amount of molecules that you are probing. And the ultimate subensemble is a single molecule or a single nanocrystal. And if you do that, you may end up getting single spectral peaks, but which are located at different locations. The same idea which I'm talking about in terms of intensity or spectra can be translated to the intensity as well, but it's very similar. But what is really the important part is that you can, once you do the measurements, a large number of measurements at the subensemble or single molecule level, you can start generating distributions of physical parameters. And these physical parameters, this distribution of physical parameters, allow you to actually generate the width of distributions, which is essentially a reflection of the heterogeneity present in the system. So essentially, doing measurements on single molecules or single nanocrystals or even the subensemble allows you to obtain the variation of properties in space and time. And it also allows you to unveil rare events and processes that are obscured by bulk. Bulk would give you a value which is the average value, but the tails of the distributions are where the rare events lie, which we can obtain using the method that I just described. And this essentially allows you to provide insights on mechanisms and also discover some new phenomena. And I'm going to talk about one of those new discovery of a new phenomena today. All our work pretty much revolves around a microscope that we have built in our laboratory. And this is an optical or a fluorescence microscope, which has several laser lines with which you can excite your sample, and you can collect the emission that originates from the sample. Either you can image them through filters, or you can collect spatially resolved spectra, or you can also do polarization resolved measurements, or you can do FRET measurements. But this picture here shows what are the different capabilities that we have. You can see we can look at colors, different colors that come out. If you want to quantify that, you can collect spectral data that is shown here on the right. Since we collect data using a CCD camera or a CMOS, it's just like our eyes or our cell phone mobile camera. You can essentially collect a video, so you can essentially look at the dynamics that is happening over milliseconds to minutes time scales. That's a huge advantage that we have. As you can see, the spectra here is evolving. And here in the middle that I have shown here, there are molecules which are diffusing in a soft material, and we can track them and you can extract information out of the system. Now, the plan for today is essentially to give you an idea of what is emission intermittency or blinking, and I'll give you a few snippets on blinking as well as something that I call flickering. And then I'm going to talk to you about the discovery of a bizarre phenomena back in 2016 to 18, and then our efforts to understand why or how. I'm not sure whether I'll be able to talk too much about what we do not fully understand yet. Now, fluorescence intermittency or blinking is something that many of you have heard about. Any fluorescent molecules such as dye-molecules, rhodamin 6G, cyanines, or aggregates of dye-molecules, these are actually covalent aggregates or fluorescent proteins, conducting polymers, or nanocrystals, the picture that is shown here on the right, all of them would actually, if you take one of them and image them, you will get an intensity that would look like this. But in reality, the size of the molecule or the nanocrystal is almost 100 times smaller than the spot that you would see. And what is more interesting, and this is basically a consequence of the diffraction limit of light. Okay, so you can't really use light to go beyond a certain wavelength scale. But if I collect a movie of the spot, you see something like this, where light's coming out and then it stops coming out. And this is the phenomena called fluorescence intermittency or blinking. And this is very, very characteristic of single molecules and single nanoparticles. And this phenomena is a temporally random process, and it can be good for certain aspects, such as super resolution imaging, which utilizes the idea of blinking of molecules, but it can also be bad for certain other aspects, which is, for instance, particle tracking. If you want to track a molecule, then if it turns itself off, the light doesn't come out, then you can't track it. Now, if you take a bunch of fluorescent molecule under ultra dilute conditions, for instance, rhodamin 6G here on the left, or some nanocrystals here on the right, and you put them on a glass cover slip and collect a movie, and then you start seeing these kind of spots. You can see it's a temporally random phenomena going from an on to an off state for semiconductor nanocrystals as well as molecules. And these fluctuations that you see are abrupt or discrete in time. That means they're very sudden in time. They're not gradual in time, all right? And this process, if I plot it, it will look like this. You can see these abrupt jumps that are going on over here. And same is true for nanocrystals. And this process essentially has been explained. I'm giving you the case of nanocrystals, is when you shine light on a system, you can generate an electron in a hole, and which is basically often called an exciton. And once it's in the exciton, when the system is generated the exciton, it can recombine, and this is a quasi-particle, it can recombine and it can emit light. And this kind of cycling process of absorption and emission, that continuously goes on. And as long as it goes on, there's no problem, light comes out. But once in a while, a rare event can happen when the electron can get trapped on the surface. And there are many trap states, for instance, near the surface or surface defects. And this electron of the hole can get trapped. And once it gets trapped, then essentially your ground state is depleted. This ball or this nanocrystal cannot absorb any further light to generate excitons. And even if they do, they recombine under non-radiative channels. So essentially, once you see the light coming out, that would mean that this process of going up to the excited state and going back to the ground state, this process is going on. And once there's, for instance, if there's a charge trapping that has happened on the surface, and then the light has been turned off, it cannot absorb or emit light, and you have to wait until the electron or the hole comes back and recombines, and you have a neutral species. And this is just one example. There are many mechanisms. This is just one of the mechanisms that have been proposed in the literature of how a blinking happens. The whole idea that why blinking is a single molecular or single nanocrystal phenomena is that different molecules, as you saw in the previous slide, and different nanocrystals, they do this transition to these trap states, these sudden or excursions or these rare excursions at different points of time. And that's really the reason why you would not see, this is not an ensemble phenomenon. This will always be observed at the single particle levels. So one of the questions that we were thinking about at one point of time is that, what happens to larger structures, such as 1D materials or 2D systems or even bulk 3D systems. And conventionally, you would imagine that bulk semiconductors, they would not show this kind of blinking behavior because, first of all, the effect of the surface is negligible. Okay, it's dominated by the bulk. And second, so what that means is that most of the carriers that are generated, they would recombine in the bulk. And the second is that even if there is some sort of trapping that's happening locally at different locations, spatial locations, you can see in this 2D crystal, they will be trapped at different points of time. And therefore, I will observe a heterogeneous fluctuation of intensities. Okay, so essentially the idea is called ensemble averaging. There will be spatiotemporally uncorrelated fluctuations would exist, and they will cancel each other out, and therefore we won't see anything. This is an example in the literature. This is back in 2005, a paper in Advanced Materials by Tsuro Kuno at Notre Dame. He showed that, can you see the movie? I hope you can. These are these CDSE cadmium selenide quantum wires, and they're quantum confined systems in 2 dimensions, but not in the 3rd dimension. And you can see these kind of fluctuations. The same group actually also looked at it's a 2D system, single layer reduced graphene oxide, where you start seeing this small little fluctuations. And if I plot the intensity, you will start seeing the spikes. And these spikes are essentially not uniform over space. They are uncorrelated as a function of space. The events that happen at different points of time at different locations are not correlated. And they're multi-level fluctuations, which I would rather call flickering rather than blinking, right? So essentially the idea that we realized back in 2018 or so, or 17 or so, is that, there are almost no reports that were there at that point of time where, you would see some sort of a uniformity in emission. There's a heterogeneity of emission in bulk systems or extended structures. Now, switching gears a little bit to perovskites. So, perovskites were discovered back in 1840s, okay, I think 1839. In Russia, there are these crystals. They have a certain crystal structure. There are these ores. Basically, calcium titanate was the structure that people thought these are people often use the term materials, but they're actually some sort of a structure. And they have this ABX3 molecular formula. And this is an example of all inorganic perovskites on the left. And this is, for example, cesium lead bromide. You can also replace the cation cesium with an organic group, and you can have, for instance, methyl ammonium lead bromide, the structure of which is shown here on the right. It can be bromide, it can be chloride, it can be iodide. So you can change the halide groups in these materials, and you can end up getting different colors. And this was actually shown very, very beautifully by Kovalenko back in 2015. He generated these variant wide color gamut of nanocrystals and the very narrow, very sharp spectra, and he could control the emission from 400 nanometer all the way to 700 nanometers in the entire visible region. You can see how sharp the absorption peaks are as well. Now, the great thing about these perovskites, all inorganic perovskites, is that they have very high absorption coefficient and very high fluorescence quantum efficiency and very long lifetimes. Okay, and so this serves as one of the essential components that you need for solar photovoltaics. And this also related to something called this carrier diffusion lengths or diffusivities, which people have shown is very long or very high. These diffusion coefficients are very high for these photo-generated carriers for these perovskites. And so this does some of the very, that's why these perovskites are basically being touted as being used for next generation solar photovoltaic materials. Now, the other thing that I would like to mention is this chemical modifiability. I have already given you the example. As you change halide, what happens? Even if you change the cations, for instance, going from cesium to methyl ammonium to formaldinium cation, you can end up getting different chemical compositions. You can vary the size also, and you can change the spectral behaviors. You can change the shape. And this is just an example from another review article by Liberato Manna, which it's in Chemical Reviews, which talks about what are the different kinds of structures that you can form, and you can generate different colors of light, again with very narrow spectrum. But back in and by the way, I mean, this is something that is very relevant for light emitting diodes, and that's why these systems, these perovskites, are also being explored as possible LED materials, and there are tons and tons of papers that we published on that front. Now, back in 2015, once this paper came out by Kovalenko in Nano Letters, at that point of time, we had already started exploring, along with Anshuman Nag, on the behaviors of single particles of these materials. And this was interesting because at that point of time, no one actually have reported anything on what the single particle properties are going to be and what the blinking propensity of these materials are. What is the photo or atmospheric stability? Because this is something that people have been thinking that this is one of the negative things about perovskites. When we looked at these, this is a kind of work with Anshuman, and this was published in Angewante back in 2015. We looked at these 11 nanometer size nanocrystals, and we found out they were extremely bright. They had very, very narrow spectra. But more interestingly, once we put them in the microscope and we looked at it, this is what we found out. Again, I'm going to show it again to you. Light is always being on, and once the light is on, even then you start see like them popping up, like turning on. It's like you are in the evening and you are sitting in the mountains and it's slowly getting dark and you start seeing the stars one after the other. These are actually individual nanocrystals which start emitting light only after a certain amount of illumination. This is under air and moisture, and we can repeat this experiment by keeping it in the dark and then redoing the measurement. We see a similar behavior, which tells us that there is something to do with the atmospheric constituents absorbing on these nanocrystals, and they can affect this what kind of defects. Their desorption and absorption and desorption can basically create or remove defects, and that can change its emission properties. But once we start illuminating them, and this is actually a movie for those who cannot see, but this is what I have shown here on the left is actually a movie, and you can see that very few times you actually see blinks. It's almost they have stopped blinking. In fact, almost a 90% or 85 to 90% of the nanocrystals show this suppressed blinking behavior. So again, I'll call this flickering. Essentially, this tells you that it's indeed blinking, but the blinking timescales are very fast. They are turn off timescales, which are represented by these long durations of off times here. They are typically sub-milliseconds or so. And this is, again, one of the very, very interesting aspects of these perovskites. What we found out that when we introduce more and more moisture, these kind of long off states or real blinking behaviors start popping up. So that means these moisture or oxygen from atmosphere can create some sort of surface traps which are non-radiative in nature. Okay. Now going back to extended structures. Now, I was working with Shaibal at that point of time, and Shaibal was one of the Sharkar in our institute, was one of the first people in India to work on perovskite materials, and he was trying to make films, and he was making these films on a glass surface, and this is an SEM picture of those films, and these are methyl ammonium lead bromide, and I'm going to abbreviate methyl ammonium CH3NH3 plus as Ma. And as you can see here, their sizes are in the order of 2 to 6 microns or 8 microns in diameter. They're very thin. They're about, about micron, sometimes microns, sometimes half a micron thickness. And they again have some spectral characteristics in the deep red region. But they're polycrystalline discs, essentially like mesa or discs, and they're more than few hundred nanometer height. And that tells you this is the bulk material that we are looking at. When we took these and put it in our microscope, and this is a blow up of the microscope that we use, again, we put it here and then we illuminate a certain region and we start seeing a picture which looks like this that is shown here on the right. And remember that in this particular epifluorescence microscope, we are illuminating everything together. It's not a point excitation. You are not doing a point scanning like a scanning confocal microscope, all right? So once we looked at this, it looks almost like biological cells, and I was like, oh, what are we looking at? And then we realized, no, these are actually the crystals that are formed or that have formed on the surface. And more interestingly, once we started looking at their dynamics and we collected videos, we started seeing some strange things. If you look carefully, you will see that in this particular region, there's a sudden wink that happens. And if I blow it up again for another crystal over here, you will again see that there you go. It stopped. There you go again. it's basically winking and is coming back. And this behavior was not only there for the doped system, but also we doped it with thiocyanate, but also for the MAPBI3 as well. We would see these fluctuations. And the difference between what I told you earlier and now is that here, every fluctuation that we observe, it is happening on top of a background level. And here you also see some sort of a multi-level jumps between states, all right? So we attributed these to the funneling of carriers through some sort of a defects that are formed locally in a local nanodomain, which is formed and it quenches the emission or quenches the carriers. And then somehow there's a saturation of these defects that leads to the emission being started back on. And this was a paper, I think this was one of the first papers, I believe, that we have, in the literature where we showed that in a bulk material, there can be local domains which can undergo blinking. That was in Journal of Physical Chemistry Letters. Now, we were not the first people to observe blinking in nanocrystals of perovskites. In fact, Ivan Shablikin's group from Lund University, Sweden, they were looking at these 200 nanometer by 30 by 30 nanometer rods of perovskites. And they were looking at these individual rods. And once they looked at them, they started seeing these huge jumps in blinks. And they attributed, they had a model, and this was published in Nano Letters in 2015. And they attributed this phenomena to migration of charges to some sort of a quenching site. Okay, it's a quenched emitting site is there, or a quenching position, quencher is present. And this quencher essentially can appear or disappear without that kind of a behavior. There is no way you can explain, why they would blink. Now, at that point of time, we were exploring other, halides of methyl ammonium lead, halides. And we were not only looking at iodide, we were essentially thinking that, okay, there are other halide perovskites where high mobility of charge carriers have been reported, right? And this is a paper in Science by Henry Snaith that talked about more than 1 micron, diffusion lengths that were reported for bromides and halides. Now, at that point of time, we started looking at different structures or bigger crystals or micron-sized crystals of these materials, which look mostly at bromides as well as iodides. And iodide came, we realized that a lot of people were working with iodides, and we started working with bromides. And then it was very, very easy to make. It was like you can take a little bit of a solution and you can put them on the surface and let them evaporate. You don't need to do too much of heating and they will form these crystals. I am basically what I use the term, I'm a synthetically challenged chemist. So it is my students and, Shaibal students, they did the synthesis. And once we created these crystals, then we realized that again, they were bulk crystals, all right? And they had very nice spectral data, spectra, and these are bromides. There's no quantum confinement in these systems. And once we looked at these on our microscope, we started seeing something very funky. And this is an example of what we did see. We started seeing that individual crystals, they are not joined, they are isolated. They are blinking vigorously. Okay, this is a real-time data that I'm showing you. And not only that, if you notice carefully, they all blink in different manner. That means this is not an effect of my excitation laser fluctuation or my focus drift or anything. It's a multi-level blinking that is happening. And if you look even more carefully, what you would start seeing is that entire crystals, which are simultaneously illuminated by our laser light, they seem to be undergoing this fluctuation together. And this is what I would now call a spatially correlated blinking behavior. As you can see, if I look at position 1 to 2 to 3 to 4, which are almost 1 micron away from each other, even if I plot the emission intensity as a function of time, I would see that the peaks and valleys and the jumps that you see, they all come together. So it was very, very bizarre and intriguing at that point of time, because it seemed that these entire crystals were blinking or flickering as if they are single nanocrystals or single quantum dots. However, there is absolutely no quantum confinement in these systems. If you shift to even crystals which had conjoined or fused grains, as you may have seen in the SEM picture before, you can see that as they're growing, they can get connected and they can get fused. We thought that, okay, in these things, this kind of behavior should not happen, but this is what we found out. Of course, this is a different grain, not the one that is shown in SEM. And you will show this kind of a sparkling behavior intermittently. There's a huge burst of photons coming out. And if you look at the grains 1, 2, 3, and 4, there are huge areas that I'm talking about. And you can see they have very, very highly correlated emission that is coming out. These fluctuations are correlated. And as compared to 5, which is over here on the lower right corner of the movie, you will see that behavior is completely different from that of the fused grain systems. Now, is it true only for this kind of disks? We started exploring other systems, and we created, Tejamani came in the picture at that point of time, and he started making rods. And again, I don't want to go into the structural and other characterization of these rods, but he made these single crystals, which are perovskite single crystalline rods. Again, they are bulk. That is the most important for you to remember. And if you look at the rods under the microscope and you collect a movie, and if you look at, this is a rod about more than 1.5 micron or 1.5 microns here. And if you look at the region 1 to 2 to 3, about 1 micron separated, look at the fluctuations. They are highly, highly correlated. We developed methods to quantify this correlation, and I'm going to use the term a blinking correlation or correlation in blinking. It's some sort of a cross correlation function that you can generate from this entire along the length of the rod, which is a pixel by pixel correlation that you can generate. And you can see it's all red. It's highly, highly correlated. And if I take the entire rod, if I take the intensity along the long axis of the rod, and then I start plotting from a movie, one frame, I put it adjacent to the previous one. And if I keep doing it for the entire duration, you see this kind of behavior. You see that over the entire space, each of these rows here, 1, 2, 3, 4, 5, each of them represent the rod. And you can see over entire space, the blinking events are spatially correlated. So it's not something that is only true for this disk. This also seems to happen for these rods. And this is an example just to show you what a correlated blinking rods mean. This is a movie. As you can see in this movie, everything is kind of fluctuating together. And if you plot the intensity as a function of time from, again, these 3 places, you will see they are almost nearly identical. Now, the correlation is very high. For longer rods, you start seeing fluctuations, which are, this is a rod which is, again, an isolated rod, which is blinking more vigorously. But here you start seeing some small deviations in these blinking behaviors. You can see that there are events where the amplitude of the blinking is low or high, but the events of blinking are still temporarily correlated. Under these circumstances, you do see a slight decrease in the correlation, but it's still very highly correlated. So the question is, what is it that this leads to this kind of a spatiotemporally correlated optical instability? And the main questions that we wanted to ask was, how is it possible, or how is it happening, and why is it happening? All right, that is the question that we thought. Now, one of the things that we realized quite early on, and that you have to invoke the idea of some sort of a metastable non-radiative trap. Because without invoking the idea of a metastable non-radiative trap, you cannot explain blinking in certain types of systems. For instance, this is actually borrowed originally from the idea of Paul Barbera's science paper on conducting polymers, where he said that in a conducting polymer, you can have many segments or many chromophores. These are multi-chromophoric systems, but even then they blink. And that's because you can have energy transfer from different segments to the lowest possible energy segment. And the same idea was used by, or an extension of this idea was used by Ivan Shevlikin first in some nano aggregates, which I have not shown here, as well as in perovskites, where he coined the term super traps. Now, these super traps are essentially traps that can quench or take off the electrons and holes that are photoexcited. They can quench non-radiatively over large zones. So the idea that we kind of came along is that also is that you must probably generate, let's say that you have generated one quencher, and if this quencher has some sort of a zone of influence, which is comparable to the size of a rod is easier to understand as compared to a disk. So I'm giving you a pictorial representation using a rod. You can have these quenchers can somehow, or these quencher can somehow take off or non-radiatively deactivate electrons and holes from this entire rod, all right? And of course, if the zone of influence of this quencher, which I call ZIQ, is much smaller than the length of the rod, then you will only see some sort of a correlated blinking happening locally within a certain region. So in a disk, you can imagine that you have a quencher that is active for some time, a special quencher, and that kind of takes away electrons and holes. Excuse me, I'm sorry, this is an error from my part. And they non-radioactively deactivate. So the main idea that I want to convey here is that you can never have many such quenchers being active at the same time. You need to have very few of them, CCs being together, because if there are many of them, then you will never see the blinking phenomena at all, okay? Because many of them can be active, and so there are always going to be some of them are always going to be active, or one or others are going to be always going to be active, so you will never see. You can also, unlikely that is only have one, because if you only have one of them, then you will only see very clear two-state kind of behaviors, which we don't see. We see more like what Paul Barber reported in 1997 in Science in the case of conducting polymers, all right? So one of the questions that we asked at that point of time is, how are we generating these things? If you remember in the beginning, I talked to you about how moisture and oxygen in the presence of light can remove or create defects in these nanocrystals. So we did a similar experiments, and in our microscope, we actually have an ability to do in situ measurements on top of a microscope, which is an enclosed chamber. And once we did this measurement, we could show, along with Shaibal and his student Anshuman, that we need some amount of moisture and oxygen in order to have a very vigorous blinking. So that means that oxygen and moisture and light, this is very important. Light is also needed. All of them together are creating some sort of a species, some sort of a very likely to be a highly charged species, which can attract the electrons and holes and recombine them radiatively. The second aspect is even more interesting, and that is that if you imagine that you have a big structure, and how does it, like for instance, if I keep my pointer to the left and keep pointer to the right, then how do the carriers that are generated on the right here and the left here, how would they communicate? I mean, if they have to recombine together, or then there has to be some form of a communication. It's like if you are in your office and you have internet as not working, you go to the next office and find out whether the internet is gone down there as well or not, right? I mean, if it's gone, that means, okay, that's an overall problem in the system. But if the other person has an internet in the next room, then probably it's a problem with your computer, right? This is a simple inference that you can make. So you need to have some sort of a communication between these photocarriers. Now, these electrons and holes that are generated in a semiconductor material is unlikely to be delocalized over the entire crystal. That is unlikely to happen. If it was a case of a metal, I would have imagined that, okay, they are delocalized, so there's some sort of a connection. The other thing that we thought about, if you remember, we had this edges of this nanocrystal were more emissive. So we explored ideas of whether they are waveguides or they are exciton polaritons that are generated that can. But the most important, or the most, I felt that the most relevant was the idea of carrier diffusion. Because in these materials, the carrier diffusion lengths are very high in the order of few microns. and the carrier diffusivities are also high. And our experimental observation was that blinking is not synchronous beyond a few microns. Okay, for very large microns. And this is just an example of rods. On the left, you see a synchronous blinking. On the right, you see blinking or fluctuations that are happening, which are spatially not really correlated beyond a certain length. All right. So we explored this idea that, okay, is it possible that it is actually about the correlated motion or the correlation diffusion of carriers. So how do you test that? How do you really test such long range energy migration? Here we are talking about microns, okay? We are not talking about nanometers or tens of nanometers or even 100 nanometers, right? So what we thought and what we found out that in the literature, there's a very nice way or a simple way that Professor Vanden Bout of U Texas Austin, and there's another connection. He happens to be either a postdoc or a graduate student of Paul Barbara, um, whom I respect a lot. He showed that if you actually take your microscope and remove one single lens, which is the focusing lens, then you can essentially convert an epifluorescence microscope into a confocal kind of a excitation. And once you have a confocal excitation, now typically confocal microscopes have a point detector, and epifluorescence microscopes have a CCD camera like your cell phone camera. But if you use a CCD camera, then what you can do is that you can locally excite the system. And then if there is carrier migration, then you should be able to visualize it because there will be a spread of the emission away from the excitation zone. So I call this, as in India, we call it a hack, or I call this a cheap man's way or cheap person's way of detecting the emission which is coming from beyond the excitation zone, provided the lifetime of the system is of the photoluminescence lifetime is high. If the photoluminescence lifetime is very small, then the carriers would not be able to migrate and recombine. Before that, they would go back to the ground state, and which we found out, luckily, that it was quite high for these systems. So here's the experiment. We locally excite it. Once we locally excite it, we can use filters to look at the excitation profile. And then we look at the emission, which is shown in the green using another filter. On the top here is shown a wide field image where everything is excited together. In the bottom here in the blue, this is where the excitation point is. And when we look through a camera or through an eyepiece of a microscope, we see the entire crystal. Exact same thing happens when it comes to the rods. You can see I can locally excite it. This is the entire crystal is excited with the light. There's a defect there in this zone. But when I locally excite it over here in this bottom panel on the right, then you start again seeing emission coming from beyond the local excitation zone. So essentially that tells us, kind of gives us that there are three different lifetimes or time scales that we're talking about. One is radiation recombination, one is the correlated carrier migration, which we believe is the dominant pathway, but there are other pathways such as waveguide assisted photon recycling that also happens. Don't want to go into the details, but I think the slowest step is the formation and the annihilation of these quenchers or these traps. And so imagine that you have no traps, the crystals emits, you have one single trap, then you have these carriers would get drawn, the correlated motion towards the strap, and there's going to be some sort of a quenching. When the quencher deactivates or it disappears and some sort of a special quencher, then the light emission of this entire crystal restarts. Right? So this can also explain this multi-level scat flickering instead of one. We believe that there are multiple traps that are formed, not too many, neither too many, nor too few. So only a few of them are active at any given instance, which gives this kind of multi-level fluctuations on top of a background intensity. I guess I have 5 more minutes at most, so I'm just going to quickly go through a few things which are interesting, which are some very rare yet bizarre events, which we had a hard time figuring out over the last 4 years. And that is about how things change with time, how the blinking propensity of this correlated blinking behaviors change with time. This is an example that I actually had earlier shown you. So I'm kind of showing the same thing again here. But if you look carefully in this entire rod, you will see one segment on the top left, which is kind of undergoing a correlated a blinking behavior. And then there's this bottom left right segment that is also undergoing a correlated blinking behavior, as you can see from the correlation matrix. But however, if you look carefully, there are events where entire rod, which spans from about here to about here, almost the entire part of this movie that I'm showing you here. This is about more than 2 microns. This is about 3 microns or so. They kind of blink together. All right. So sometimes, let me give you another example. This is a situation where we have two fused grains, 1 and 2. And if you look at these two fused grains, and if I plot the map, the correlation map, you see clearly that each fused grain is highly correlated behaviors. Can everybody see this? I hope they can. So, but not the 1 plus 2 together. And if I look at a trajectory, the intensity of grain 1 and grain 2, so I would like you to only look at the green and the red curves that are shown over here. X-axis is time, y-axis is PL intensity. You will notice that in certain region, up to 10 seconds, there's a clear correlation of the blinking between the two grains. But beyond, and of course, these are just blow-ups to show you that these correlation events exist. But beyond 10 seconds, 10 to 25 seconds, this correlation seems to have lost. And this is something that really perplexed us. And after a lot of thinking and doing some experiments, we came up with a model. I'm cutting the long story short here. And this is what we believe is happening with some evidence that if imagine you generate some of these quenchers or these charged species at the interface of these fused grains at the grain boundaries, then what would happen is that otherwise the carriers were free to move from one grain to another. But then once you form some sort of a barrier in between these two grains, then these two segments become disconnected, electronically disconnected in some way. And that essentially makes the blinking of the grains uncorrelated. And that is what we think is going on. Now, there are more weird events that happen, which although we have published the data, maybe for people to see, and so that they can give us some hints of what may happen, may be happening, are these strange anti-correlated behaviors. If you look at these fused grains, there are 1, 2, 3, 4, 5. I want you to focus on 1, 2, and 3 here. And if you look at 1 and 2, that's what's plotted here. And you can see from 0 to 4 seconds, there is no correlation. In between 17.5 and 20 seconds, there's clear correlation between the grains. But, so this is uncorrelated. On the right is correlated, positively correlated. But you see what's happening between 16 and 17 seconds and 29 and 31.2 and 30.2 seconds. There seems to be anti-correlated behaviors. So it almost looks like, and it's also visible from the images, also looks like there's some sort of a directional energy flow, carrier migration from one grain to the other. Now, I cannot explain why such a behavior would be observed, and I still do not have a concrete explanation for that. Currently, we are also exploring another option, but that is something that I think I should not discuss in the interest of time. And that is essentially we are working on to figure out what is the effect of 1, 2, and 3 quenchers and the distances between the quenchers and the traps, and how they can be used to explain whether a correlated behavior would be observed or an uncorrelated, spatially uncorrelated blinking behavior would be observed. But maybe that is something that we'll keep for another day. That's another story altogether. So let me quickly, I don't want to talk about a big conclusion or series of conclusions here, but I think one of the take-home messages is that uh, what we teach in our classes, even in my single molecule spectroscopy course, that or what I had been teaching till 2018, is that that blinking is basically a hallmark of single emitters and single nanocrystals. That's not necessarily true. You can observe blinking even for larger objects, quasi 1D or quasi 2D or 3D objects. And it depends. It depends on the material that you're using, whether there's electronic communication there from different positions or not, and what is the density of traps that are formed, and whether those are natural traps or whether they are formed by light as well as in the presence of oxygen or moisture. And that's of course leads to the question that how can we potentially apply this? Can these phenomena be used for new devices? Remember, we are talking about a communication over a length scale of microns, so it's very, very interesting. Um, sensors, can we use this phenomena as sensors for the detection of water or oxygen molecules? And that's also kind of an open question. I work mostly in basic sciences. My research interests are to understand fundamental processes, but this is something that I have been thinking, and we are also exploring a little bit in that direction. Um, but more importantly, I think that, I think people need to also explore other you know explanation. Is there any other possible explanation which we have missed out, and maybe somebody else can come up with a better explanation, which kind of where all the experimental data can be explained, and the bizarre phenomena can be essentially be understood or comprehended in much more detail. All right, so this is my last slide. What I'd like to mention regarding the relevance, and this is a very, very recent paper by Sudipta Set, Boris Lewis, and they are working in collaboration. They are basically the groups of Johan Hopkins and at KU Leuven and Ivan in Schablikin in Lund. And there's a paper that came on very, very recently this year. They are working on actual devices. They're trying to do correlated mapping of PL fluctuations and EL fluctuations, and they are trying to see what is the extent of correlation in these grains that are used in this material. So you can see that the time scales, and I mean, I'm just trying to justify why these time scales are important. A device operates in the time scales of seconds to minutes. All right. We observe fluctuations in the same time scale. So, it is very, very important to understand what are the real reasons why such fluctuations happen. If we can stop it, if we can reduce it, can we increase the efficiency of devices? And I think I'm not a person who works on too much of applications, but this is something that I wanted to flash. And this poster is from Sudipta's poster, who came to Bombay in a recent conference, and that is where I saw this, but this paper is published. So those who are interested, feel free to go and have a look at that. Again, thank all my collaborators and students, and of course, everybody else who are listening patiently for 45 minutes. And before I end, I would also like to kind of do a little bit of advertising for a journal, ACS journal, which is Chemical and Biomedical Imaging, in which I am an editorial advisory board member. And this is a relatively new journal. It has been started for about a couple of years now. It has not finished 2 years. It's an open access journal which basically focuses on uh, imaging, and with chemical and biological imaging. There are we publish fundamental as well as applied research, review articles, reports, everything. The editor-in-chief is Professor Zhijian Kuo from Nanjing University. This publication is actually a collaboration between ACS and Nanjing. And as you can see, there are various areas here: imaging probes, optical imaging, electrochemical, mass spec imaging, nuclear imaging. So various, not just optical aspects of imaging, MRI and magnetic resonance-based ultrasound interference. So everything together, and these applications in both chemistry, chemical science, and related subjects. For instance, it's a call for papers in imaging in energy science. There's a call for papers in bioimaging of metals, and also AI tools or artificial intelligence based tools for chemical and biomedical imaging. I think this is a great area that's coming up. It's sort of a lot of impact in the field. So there's a focus journal which on imaging, which currently doesn't exist in the ACS group. Of course, another thing to mention here is that this particular journal, all the APC, the full form of it is publication charges are waived for all articles submitted by 31st December 2025, which is end of this year, provided, of course, it is accepted and after peer review. So with that, I'd like to end this talk. And again, I thank you profoundly for being patient and for your attention. Thank you so much.